In this question, we assume that there are 365 equally probable birthdays. For simplicity, we can assume that the birthdays are given by number 1, 2, 3, and so on, up to 365. By equally probable birthdays, we mean that given any one person, the chance of having a particular birthday is 1 over 365. Here we have a group of k different persons. The question is to find the probability that all of them have different birthdays. So the first thing we need to do is to describe the sample space. How do we determine the sample space in this question? Well, there are exactly k different persons, and we can write down their birthdays in a k-tuple. Meaning the first entry of the k-tuple will be the birthday of the first person given by xi, so where x1, sorry, where x1 is one of the number 1, 2 up to 365. The second entry is the birthday of the second person, denoted by x2, and so on up to xk. So we have k entries, each one corresponding to the person, and each xi is taken from the set 1 up to 365. So these are all the points in our sample space. Next, we want to describe the events that we are interested in. This is the event that all of them have different birthdays. So let us denote the event by E. So this is the event that all the persons have different birthdays. Right. How do we describe the elements in the events E? Well, these are the k-tuples such that all the numbers xi are distinct. So all xi are distinct. Because we want all of them to have different birthdays. Now let us calculate the size of the sample space and the size of E respectively. If we denote the sample space by S, then the size of S can be calculated as follows. We can first count the number of ways that we can choose x1 from the set 1 up to 365. Well, there are 365 choices. Next, we choose x2. Again, since there are no restriction, we can choose any number from 1 up to 365, and so on. Therefore, altogether we have 365 to the k, right? Because there are k terms altogether. This is the size of the sample space. Next, we want to count the size of the events E. We can first count the number of ways to choose x1, right, before choosing the other entries. There are 365 choices for x1, since this is the first entry we are allowed to choose. Next, since we have chosen x1 and we want x2 to be different from x1, we are left with 364 choices. So the next entry will have 365 minus 1 choice. Um, for the next element x3, since it has to be different from x1 and x2, we have 365 minus 2 choices, and so on. In particular, for the last entry xk, we have 365 minus k minus 1 choices. We can write this in the following way. Notice that the number decreases by 1 until we have the number 365 minus k plus 1. So in terms of factorial, this is 365 factorial over 365 minus k factorial. So now we have the probability that all of the k persons having distinct birthdays is equal to the size of the event E divided by the size of the sample space. So this is the expression for the probability of the event E. Our question is the following. We want to find the smallest number k such that in a group of k persons, the probability that at least 2 of them having the same birthday is more than half. We need to describe the event in terms of E. That is given by the complement. Since E is the event that all of them have different birthdays, therefore the complement says that at least 2 of them have the same birthday. We always have a group of k persons, so k is always fixed, so the complement of E is at least 2 persons have the same birthday. Therefore, the question becomes finding the smallest k such that the probability of E complement is strictly more than 0.5. All right, we know the expression for the probability of E. Also, we know that the probability of E and the probability of the complement sum to 1. So we can write the left-hand side as 1 minus the probability of E more than 0.5. Instead of solving this algebraically, we are going to find this by tabulating the values for different k. Here are some probabilities for the event E and the complement for different values of k. We notice that the probability for the complement of E increases as k increases. So eventually this probability will be more than 0.5, and this happens for the first time when k equals 23. For all the other values of k which is below 23, the probability will not exceed 0.5. So all the probabilities here will be at most 0.5. Here we did not compute explicitly the probabilities. If you like, we can compute this using some computer program. Be careful if you compute these values using the calculator, because due to truncation error, the values that you get may not be accurate. All right, we conclude that the smallest k, such that the probability of E complement is more than 0.5, is k equals 23. In other words, in a group of 23 persons, we can conclude that the probability of having at least 2 persons with the same birthday is actually more than half.